Hi folks, welcome to this lesson on differentiating logs and exponentials. We're working from the old book, the Hayes Mathematics for the International Students 3rd edition book, and there are work solutions for that, so any practice questions that we reference will be from in there. So here's our new rule. The derivative of e to the x is e to the x. That's about as easy as it can get. So you might say, well, does that work for every other base? No, it doesn't. It only works for the base of e. And remember, e is roughly 2.72-ish. It's actually defined by this limit. It's the limit as n goes to infinity of 1 plus 1 over n to the power of n. And we looked at it from compound interest a little bit last year. But any number k can be rewritten this way, e to the ln k. It's just the number k. So e to the ln 2 is the number 2. We secretly have a way to deal with any base. But with that said, we prefer the base of e. Notice that we always need to look out for the chain rule, functions that have an inner and outer part. So it follows that the derivative of e to the f of x is just the regular thing, e to the f of x times the derivative. Okay? Or maybe a better way of saying that is e to the glob becomes e to the glob, okay, times the derivative. Now in your formula booklet, you're only going to be given essentially this version of the rule. You always have to be looking out for the chain rule. So let's differentiate a few. Okay, e to the x is just going to be e to the x. So let's think about this one. Y equals e to the 3x. So that's e to the glob. The derivative will be e to the same glob times the derivative. Okay, so it's like the outer part of this is the e to the 3x, and the inner part is the 3x. So that means we have e to the 3x times the derivative of 3x, which is 3. In other words, 3 e to the 3x. Same sort of idea here. If we have y equals e to the x squared minus 1, that's e to the glob. So its derivative is just nothing changes, e to that glob times the derivative of that glob. Okay, so that's e to the x squared minus 1 times 2x. Or we could write that as 2x e to the x squared minus 1. Notice how the exponent has not changed. Okay, so when we have something like this, x squared, that goes to 2x. That is not an exponential. That's a polynomial or a power function. It has the x in the base. An exponential is one where the x is in the exponent. So same deal here. We have e to the glob. But we might want to rewrite this in the form that says e to the 2x plus 3 all to the half. So we have e to the glob. This is our whole glob. So our derivative is going to be y prime is e to that same glob, which would be 2x plus 3 all to the half, or square root of 2x plus 3, times the derivative of that glob. Now here's something to notice. This is probably the first time this has happened to us. The glob itself has some globiness, right? It has a power of a half on the outside and then an interior part of 2x plus 3. So when we differentiate that glob, we're going to have a half, 2x plus 3 to the power of negative a half, times the derivative of its interior, which would be 2. Okay, so we have to keep on sort of working our way inside. And if we simplify that, I mean, I guess we could write it as 2x plus 3 to the negative a half. You can see that half and the 2 divide out, all to the e times e to the 2x plus 3 all to the half. Or if you wanted to get fancy, which is optional here, y prime would be e to the root 2x plus 3 all over root 2x plus 3. That's very nice like that. Okay. But globs can have layers of globiness to them. At its very most exterior level here, though, we're thinking about it's e to the something. And then we find the derivative of that something. Next one, y equals x squared times e to the 3x. When I say it out loud, I recognize that this is a product. Or you can think of it as it's two x's that are not separated by by an addition or subtraction. They're multiplied together, so there's no plus or minus between them. So I'd be thinking u is x squared, v is e to the 3x, which means e to the glob, so u prime is going to be 2x. That's just basic stuff there. And v prime is an actual exponential, so it's going to turn into e to the 3x times 3, right? Because it was e to the glob, so it becomes e to the glob times the derivative. Or v prime is equal to 3e to the 3x. And product rule is u prime v plus uv prime, or that's how I like to think of it anyways. So I have u prime v plus u v prime. I could get rid of some brackets here. 2x e to the 3x plus 3x squared e to the 3x. And then where you go from there is up to you. You could leave it like this. If you really wanted to factor it, you could. There's the greatest common factor here of x and also e to the 3x. So if you take that out, you get x e to the 3x. You'd just be left with 2 from the first part. And you'd be left with 3x from the second part. And it turns out that kind of form is going to help you figure out where you have zeros on your slope, which may be helpful to us. All right, this last one. So this requires a little bit of creative thinking. And it may give us some insight into how to generate a rule. So you might be saying e is not my favorite number. 3 is a better number. I don't know. I think e is a pretty awesome number. But 3 is equal to e to the ln 3. We dealt with that at the start of the notes. So this whole thing, I'm still writing y equals, okay, because I'm not differentiating. I'm just going to write it in terms of e. So that means y is, when you have powers to powers, you multiply them. So it's ln 3 times x. Okay, that whole thing right there, that is means 3 to the x, just written in a weird way. So now I can differentiate it. E to the glob is going to become e to the same glob, okay, times the derivative. Now, you might get confused here. Ln 3 times x. Well, ln 3 is just a constant. Think if it had said 5x, the derivative of 5x would just be 5, or 5 times 1. If it had said 7x, the derivative of 7x would just be 7. If it said pi x, the derivative of pi x would be just pi. Ln 3 times x, ln 3 is just a coefficient. So its derivative is going to be ln 3. Okay, so that is the derivative of the glob. And so we get ln 3 as our derivative. So one way you can write this final answer is ln 3 times e to the ln 3 times x. Okay, that's all up in the exponent. But we know from sort of the third step that this part here really just means 3 to the x. So you could write your final answer like this. Ln 3 times 3 to the x. Okay. This isn't going to come up that often because we tend to try and work with bases of e. But if you wanted a rule here where, just like for e to the x, we wanted to figure out if you have an original one, if we have a to the x, where it even could be e, but for any base, what you're going to get for your derivative is still an exponential, but you have to pay a tax out front, okay, of ln that number in order to pay for the privilege of using a base that is not e. If you had e as your base, well, out front you just have ln e, which is just 1. Okay, so the rule is easier if we have e's. Easier. Ha, 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 ha. Find the gradient of this at x equals ln 2. So this is clearly a quotient. U is going to be your top. Okay. V is going to be your bottom. U prime would just be e to the x minus 0, so just be e to the x. V prime would be e to the x. And the derivative of a quotient is u prime v minus uv prime all over v squared. So for us, the derivative anywhere is going to be, let's just work this through, u prime, that's e to the x, times v, which is e to the x plus 1, minus u, which is e to the x minus 1, v prime, which is e to the x, good grief. And then we'd have that all over e to the x plus 1 all squared. Okay. Now we could multiply stuff through here, but I notice on the top that I definitely have a greatest common factor of e to the x. It's in both of these terms. So I'm going to take it out just to make it prettier. You don't necessarily have to, but I think it will make my life a little bit easier. So e to the x, what would that leave me with? It would leave me with e to the x plus 1 minus e to the x minus 1 all over e to the x plus 1 all squared. Let's keep going here. In those brackets, you might want to do this without showing all the steps. I am going to show the steps, though. It's e to the x plus 1 minus e to the x, and this is minus a negative, so plus another 1. Oh. And we'd actually get here whether we had multiplied out or whether we factor. So that's going to be e to the x times 2, right? Because those e to the x's will go inside the big square brackets, all squared. Or dy by dx is 2e to the x all over e to the x plus 1 all squared. Okay, that's the slope anywhere. At specifically x equals ln 2. Let's find that slope. Now we plug in. So 2 times e to the ln 2 all over e to the ln 2 plus 1 squared. Well, e to the ln 2 is just 2. We looked at that earlier on here. Any number k can be rewritten as e to the ln k because e and natural logarithm, or e to the power of and natural logarithm, undo each other. They're inverses. So if I put this in, I'll have 2 times 2 all over 2 plus 1 all squared. And that will give me 4 over 9. I don't feel that confident about this. That's 0.444, but I'll go to decimals and check it out. Actually, maybe I'll go to the GDC and check it out. So e to the x minus 1 all over e to the x plus 1. That was the original function. I got to watch out here. That plus 1 should be down here. Okay, zoom standard because I don't really know what it looks like. Okay, it kind of makes sense that at x equals ln 2, it won't be that steep. We go second, calc, and we choose number 6 for dy by dx. And then I can just tell it ln 2 for my x value. So I type in ln 2 and hit enter. And you may or may not be able to see it, but there where it says dy by dx, it's reading 0.444. And your GDC will do the same thing. That means that we've got a decimal version that's the same as the fraction that we got. In the Hayes Mathematics textbook, you could take a look at page 375, these questions here. I'm going to keep going to the logarithmic differentiation, though, as well. So here's the rule for differentiating a logarithm. If you have ln x, its derivative is 1 over x. This is for a log with a base of e. We could use the change of base rule to get around to other bases, but this ends up being most slick with a base of e, or a natural logarithm. Remember to watch out for the chain rule. So if you had y equals ln of some function of x, then the derivative would be 1 over f of x times the derivative, or derivative over the original. Okay, if you want to think of this in globular terms, if you had ln of a glob, then its derivative would be 1 over the glob times the glob prime, or original on the bottom, derivative on the top. And that's how I remember the derivative of a logarithm. It's just the original thing you had on the bottom and its derivative on the top. And I remember it with a song. It goes, original on the bottom, derivative on the top. And I have a whole song that I'll try and link in the video description or maybe even up top on this video that you can click on. It's like 3 minutes long. I've left some space here for you to transcribe the song if you're so inclined. You can do it either in treble or bass clef, or you can do it in tenor or alto clef. Up to you. But how to differentiate a log is just the original goes on the bottom and its derivative goes on the top. So original is on the bottom, deriv on the top. When you do that, the chain rule is built in. So if I have something like this, y equals ln of 5x, all I do is I think the original, not involving the ln, just the thing I'm taking the log of. The original goes on the bottom, that's 5x, and its derivative goes on the top. So the derivative of 5x is 5. And then maybe I'll simplify a little bit. Okay, so 5 over 5, those divide out 1 over x. There we go. Same thing for the next one. Here's the original on the inside. So because it's a logarithm, I go original on the bottom, and its derivative on the top. So that would be 0 minus 5, or just negative 5. Here, there's nothing that can divide out. And again, if you use the song to differentiate logarithms, then the chain rule is built in. You don't have to look for anything else. You do have to watch out for other rules. This one is x cubed times ln x. So this is a product rule. Okay, product rule does this business. And so u would be x cubed. U prime would be 3x squared. For ln x, that would be our sort of v, ln x. And its derivative is 1 over x, though you can also sing that through. The original goes on the bottom, its derivative on the top. And now we just plug and chug in the formula. Okay, the product rule says u prime times v plus u, which is x cubed, times v prime, which is 1 over x. And that can simplify a little bit. 3x squared plus x cubed over x would just be another x squared. So you could take out a common factor here. So you could say x squared times 3 ln x plus 1. This isn't the greatest way to write this, though. It's kind of unclear whether that plus 1 applies to the logarithm. So often you'd see this written with the 1 first, 1 plus 3 ln x. The order doesn't matter for addition. Or if you wanted to be really clear that it's only the x that is being, quote, logged, put some brackets around it. One of the nice things about logarithmic differentiation is, A, it's easy to remember with a song, and B, it can break apart different stuff. The real reason for the invention of logs is to make things like multiplication and division easier. And we know in differentiation, multiplication's rough because you got to use the product law. Division's rough, you got to use the quotient law. So here are our log laws. And I'm going to write them with natural logs here. Ln a to the x is equal to x ln a. Ln a times b is equal to ln a plus ln b. They work for any base, but we're going to see them most often with natural logs. And ln a over b is ln a minus ln b. So this thing over here looks like you could just sing it through. Original on the bottom. Oh my gosh, that whole mess would go on the bottom. And then its derivative on the top. But finding the derivative of what's inside that log is brutal. It has a product. It has a quotient. It has some chain rule-y stuff. So if you have an option to break stuff apart using log laws, then so much the better. So what I see that sticks out to me the most in this is that there's a big old fraction. So I will split it apart using this kind of log law first. So it's ln of that whole top minus ln of the bottom. And then I might notice that in this part here, there's multiplication. So I can split it apart using addition. And I could also rewrite that square root as x to the half. So I've used the division log law, the addition one, or multiplication one. And now I can even do more stuff. And you know what I did wrong here is I put a y prime. I should not have said y prime. I haven't differentiated yet. Okay, this is all just y. So that would be 2 ln x plus ln of x minus 3 minus a half ln x. Everything I've done here has nothing to do with calculus. It's just log laws that we already knew. Now we are ready to differentiate. Okay? And we'll have a different looking version of the answer than we would have if we had gone just sing it through to start with. But it's going to be real easy. 2 stays, it's a coefficient. And then for this one, original on the bottom, derivative on the top. Okay. Plus, next one, differentiated, original on the bottom, its derivative goes on the top. Okay. And we have minus a half, that stays. And original on the bottom, derivative on the top. And I can just do a little bit of multiplication here. But the actual differentiation is really easy if you use your log laws first. So look for opportunities to use log laws before differentiating. We'll do that in 2 last examples here. It says, careful, differentiate this one. This is the ln of 2x minus 3 all to the 4. Okay, if we differentiate it, we're going to have some chain stuff. But if we use our log laws, then that 4 can come down front. We have this. Okay, that is the log law that ln a to the x equals x ln a, or the power law of logarithms. It's not differentiating. Now we can differentiate. 4 stays, it's a coefficient, and original on the bottom, derivative on the top. Okay, and the derivative of 2x minus 3 is 2. You get 8 over 2x minus 3. If you compare that to just singing it through from the beginning, or we could just go original on the bottom, okay, and its derivative on the top. Oh my gosh, the derivative of 2x minus 3 all to the 4 is 4. 2x minus 3 all to the 3 times, there's a chain rule there, so times 2. You'll actually get the same answer, but with more pain. Okay, so you might as well use your log laws first. And so the last one is setting up a trap. Can you use the log laws here? No. In this case, it's not that 2x minus 3 is all to the 4, it's that the whole thing is to the 4. In other words, the outermost shell is power of 4. At its most basic, this one that we're looking at right here is a glob to the 4. Okay, so essentially this is glob to the 4. The other one was the ln of something to the power of 4. This is the ln of something, comma, to the power of 4. So when I differentiate it, I have to deal with the outermost shell first. It's glob to the 4, so it becomes 4 glob to the 3 times the derivative of that glob, whatever that is. And I really like this graphical approach, that it's, it's just a glob. So 4 glob 3, what is that glob? Oh, it's ln of 2x minus 3. Okay. And then times the derivative of the glob. Well, the glob itself is a logarithm, so its derivative is original on the bottom, derivative on the top. I missed the octave there. Sorry, folks. So we could write that as 4 ln 2x minus 3, that thing's all cubed, times 2 over 2x minus 3. Or we could write it as 8 ln 2x minus 3, all cubed, over 2x minus 3. Okay, so they are subtly different. If the power of 4 applies to the thing you're taking the log of, you can use log laws. If it's a power of, and then you have the logarithm on the inside, essentially it's a power on the outer shell, so you have to just deal with it like any other glob to the 4. And that leads us to some work from the old textbook, page 377. There's a for fun one in there if you want to do it. But let the song be your guiding principle for logarithms, and remember that the song has the chain rule built in.